Hello, my name's Declan Russell and welcome to the breakdown of Helios, our real-time path tracing look dev tool. The goal of this project was to create a look development tool that would produce high-quality images while eliminating render times. For this to be a viable application in a pipeline environment, we also needed to incorporate some standard to achieve compatibility with production renderers. To achieve this, we have implemented the support for ImageWorks OSL language. To begin development, I first needed to set up a number of build steps to create our application. Toby's OSL to CUDA compiler required Flex and Bison. These take in predefined configuration files and generate prerequisite files for our C++ sources. Next, Optics uses a just-in-time approach to compile any dependent optics programs at runtime. However, these programs must first be compiled into NVIDIA's assembly-like PTX code with NVCC. Our next step was to create our path tracer. In our original approach, our ray generation program would send off a ray into the scene, which would hit an object and return a radiance, attenuation, hit point, and new ray direction determined by the object's material. These would be accumulated before our ray generation program sending another ray from the hit point into the new direction. This would be repeated until either hitting a light source or reaching the user-defined maximum ray depth. However, this created a problem when having a material that may not clearly be defined but with a single BRDF. Since the ray generation program has no connection to the material program, there was no way of knowing how many rays we may have to send off and in what direction. To solve this, we allow each material program to trace its own rays recursively to compute a value to determine its color. This value will then only be returned to our camera once at the end of its recursive cycle. Unfortunately, this approach does add to the overhead of our program, as recursion is not ideal for the GPU. However, for our test, this overhead was not detrimental to our performance. For this to be a viable application, it became quickly apparent that the user would need to import complex geometry such as triangular meshes. Therefore, I have written an importer to load triangle meshes such that it can be visualized in Optics. This required writing a triangle ray intersection program so that Optics knows how to test intersections with this geometry. For requirements of the OSL shader language, our model importer also supports texture coordinates, tangents, bitangents, and the normals of a triangle mesh imported. To improve performance, an SBVH acceleration structure has also been applied to the geometry program. Another problem with GPU path tracing is the limitations of memory. This is an issue because path tracing requires all assets to be available to test ray and object intersection, requiring everything in the scene to be loaded onto the GPU. To allow the user to have as much geometry as possible in a scene, I have implemented geometry instancing, therefore requiring asset data to only be loaded onto the GPU once. This was achieved by registering multiple optics geometry programs to a single buffer on the GPU. To allow these to be independent from each other, a transform is also added to the geometry program, which when traced concatenates with the information retrieved from the buffer. When traversing around a scene in our path tracer, we found that with particularly heavy scenes, the input feedback was less responsive, often making traversal difficult and frustrating. To solve this, I have allowed the user to reduce two properties of the scene while traversing. Firstly, the number of pixels rendered in the scene, and secondly, the maximum depth of the ray. This reduced computation helps improve the responsiveness of the application, making the general user experience more pleasant. One of the key features of our application is the compatibility with OSL, such that the user can create and preview OSL shader programs in our application that can then be copied across to production renderers. To do this, I have taken inspiration from Blender and implemented a node graph to allow the user to construct their OSL shader programs. My node graph will take a user-defined node graph and turn it into an optics material program. Each shader node is created by loading in a user-defined OSL program which is translated into a CUDA kernel by Toby's compiler. My node graph then computes the order in which these are linked up to write the optics program. This is achieved by working backwards from the last node, recursively evaluating the inputs of the node until all the nodes have been evaluated. From here, I generate an optics program which calls the OSL CUDA kernels in the order that the nodes have been evaluated. This program is then compiled into PTX by NVCC and compiled into an optics material program, ready to be attached to a model in the scene. An important feature is for the user to be able to change input parameters to the shader and see the effects on the fly. By setting up these variables as uniforms to the material, the user may change these parameters and see the effects as they happen. The user may also want to create a shader program and then make changes to it at a later date. Therefore, I have implemented a material library which will save the material, allowing the user, if desired, to load it back into the node graph and make alterations. Finally, we found that having to recreate scenes every time we launch the application to be a laborious task. Therefore, I have implemented a feature to allow the user to save the scene to a file such that they can load it back in at another time.